final example of the application of concept of momentum, let me look at a variable mass problem. Where on my system of interest either the mass comes and adds on, or my system of interest is dropping some mass. A familiar example of this is the rocket propulsion, where the gases are exhausted. So, to formulate this, let me take a mass m, which is initially moving with velocity v, and onto this I add on a mass delta m, which was coming in with velocity u. If this is in outer space, there will be no external force on the system. If this is on Earth or some other planet, there will be gravitational force on the system. So, let us assume there is a net force F external acting on the system. In time delta t, therefore, the momentum change of the entire system is going to be equal to F external times delta t. Let us see what the momentum change of the entire system is. So, initially this mass is moving with velocity v, mass is m, a mass delta m, which was coming in with velocity u, and finally it goes to becomes a system of mass m plus delta m moving with velocity v plus delta v. Notice that I have taken all quantities to be positive, and that is to keep my calculations simple. I do not have to worry about any minus signs appearing anywhere. So, net change in the momentum is going to be the final momentum, which is m plus delta m v plus delta v minus m v plus delta m u, which is m v plus m delta v plus delta m v plus delta m delta v minus m v minus delta m u. This cancels with this. I combine these two so that I get the net momentum change to be delta m v minus u plus m delta v plus delta m delta v, and this must be equal to, this is a vector, F external delta t, and therefore, I have m delta v over delta t plus delta m delta v over delta t is equal to F external minus delta m over delta t v minus u, which I am going to rewrite as F external plus delta m over delta t u minus v. I do so because this quantity I then recognize is nothing but u relative of mass delta m with respect to my initial mass. So, the system that I am focusing on satisfies this equation. When I take limit delta t going to 0, this term can be dropped because it is going to have a delta t on top and therefore neglected. So, final equation that I get then from this is m dv dt is equal to F external plus dm dt u relative. Mind you, the total momentum is still changing out according to this, but I am focusing on one particular system on which the mass is adding on or from which the mass is going out. Sometimes we get confused as to what sign should be here. The best way to remember this is, in a rocket problem, the velocity always goes up, dm dt is negative, u relative is negative with respect to the rocket, and therefore this term is positive, and that is what we want if the velocity should go up. Let us try to apply this to the rocket problem. In my rocket problem, what we have is a rocket that exhausts gases, and this exhaust is at a constant relative velocity with respect to the rocket. So, suppose I fire a rocket from the earth's surface vertically up as a sample problem. Let me take this direction to be y, and therefore I am going to have for the rocket m dv dt is equal to F external, which is only the gravitational force in the negative direction, plus dm dt u relative. U relative is u j in the negative direction, and dm dt is also negative, but that I do not have to write explicitly. So, and v is some v j. So, when I transform this vector equation in terms of these quantities, I have m dv dt is equal to minus mg minus dm dt times u, and therefore I have, if I divide by m all over, I get dv dt is equal to minus u dm dt 1 over m minus g. Integrating, since u is a constant, I get v final minus v initial is equal to minus u log of m final over m initial minus g t final minus t initial, where the rocket was fired at initial time ti and went up to tf, which is same as u log of m initial over m final minus g delta t, where delta t is the time for which the rocket was fired. So, you can see that the final speed that it gains depends on the ratio of the initial mass to the final mass. Larger it is, more it will gain, and if larger delta t is there, the gravitational force slows it down, and therefore you want to fire the rocket in as short a time as possible. And that is precisely why when a rocket is fired, which you may have seen a PSLV going up or ASLV going up, there is a lot of fume, lot of fuel is burnt right in the beginning in as short a time possible as they can. So, what we have seen so far is that we have introduced the concept of momentum. We have seen that the momentum satisfies the equation dp dt is equal to F external only, irrespective of what the nature of force between the particles in a many particle system is. The only requirement is that Newton's third law is followed. This is a requirement. There are examples where it is not followed, and I will let you think about it. Third, we saw therefore that if F external is 0, the total momentum is a constant, and that helps in solving problems, as we will see in the coming few lectures. We also introduce the concept of center, let me just bullet them, of mass, and saw that this is a point which keeps on moving as if there was the total mass m sitting at this point. And finally, we looked at the variable mass problem. I would urge, because I will be using conservation laws in the coming few lectures, that whenever you apply conservation laws, you should also try to look at what is going on. For example, in the rocket problem, after all, rocket gets propelled in this direction because there is a force that is pushing it. So you should ask yourself, where is this force coming from? Although I can get my answer, I can solve the problem in a very easy manner if I apply conservation of linear momentum, but you should look for how does this force arise. Let me look at the rocket problem. You see, what is happening is this gas inside which is being burnt, or the fuel which is being burnt, applies pressure all over. As long as this side is closed, the pressure on this side, whatever forces applies, balances the force on this side. The moment I open this side, this part is removed, the gas is coming out. So the force on this side is not balanced, and consequently rocket starts moving in this direction. Let me then end this lecture by leaving you with a similar problem. Suppose I take a box which is evacuated, there is nothing inside it, and I punch a hole here. I let you think, which way should the box move? Should it move to the right? Should it move to the left?